Seeing machine learning through the perspective of system 1 and system 2 allows us to compare machine learning models with human cognition. I'd argue that we built something very similar to human cognition. I did this in my previous video as well. It was less in-depth. It was less technical, less theoretical, and I like to dive into that because I think these priors are important to have in order to accept the conclusions. And there's a lot of depth, but we are gonna dive deep into it. So, system 1 is intuition. System 2 is reasoning. If you're not familiar with these concepts, I advise you watch my previous video. So, imagine this. We are in this world full of data, full of dots, and we're trying to connect the dots. We're trying to find the patterns in the chaos. This is what system 1 is. It is pattern matching. Simply, how the brain does this is through Hebbian learning. Hebbian learning is the idea that neurons that fire together, wire together. Of course, this is very useful. When we hear a bell, when we see food, we will attach these two stimuli together. This is Pavlov. This is classical conditioning. It's unconscious, it's quick, it needs previous data, and it does pattern matching. Now, machine learning models do this through unsupervised learning. Unsupervised learning means there is no truth label to the data. It's just data. Just like we are thrown in the world with just data. We don't know what's true. We just know that there's data and we're trying to find the patterns. Now, I've heard people say, GPT models are just pattern matchers and they do not generalize. I want to state this clearly. Models before O1, they are not trained to use test-time compute to solve problems. The definition of reasoning is using test-time compute to search the search space to find the answer. Therefore, they are not reasoning, but they are generalizing. This is a very important distinction, something that's often mistaken for each other. So, the models do generalize. I've covered this in previous videos, and it's clear from literature, there's no debate about this. They are able to generalize to new data. In fact, to be able to generalize to new data is simply classical machine learning. This is not something new. We know machine learning models do this, and we do this as well. It's very expected that we do generalize from pattern matching. Just consider the fact that the world is full of patterns. It's basically infinite. For us to take in all this information, it's going to be very hard if we have a brain with limited capacity. Our brain is equivalent to a finite state automata. We could not take in all this information. This means we have to compress the information. And by compressing the information, we make the information an abstraction of reality. And abstractions have the property that they generalize well to new data. If you're familiar with old school machine learning concepts, you know a simpler function is able to predict future data better. This generalization is limited to in-distribution training data. They are not able to generalize very well out of distribution. Imagine you are taking a physics exam. There are going to be questions on this physics exam that are very similar to problems you've seen before. These problems are in distribution, meaning that they are not the same as the problems you've seen before, but they are from the same type of distribution as the problems you've seen before. They're characteristically similar, making that you can use the same methods to solve them. Now, when you get a problem on your exam that is very different from what you've learned, we call this out of distribution. Out of distribution data is data that's characteristically different from the problems you've seen in your training. In order to solve this, we cannot bet on our training compute. By definition, out of training data is not in the training data, so we could not increase compute during training. It wouldn't help. So we need compute when we see the problem. So we need test time compute, which system 1 is not. So we couldn't solve this with system 1. We can solve it using system 1, because system 2 is just an iterative version of system 1. I'm gonna explain this by talking about imagination. See, I said that models are unsupervised. More specifically, they are using self-supervised learning. This means that the truth label to their data is the data itself. So they're gonna hide the next word and predict it. And then they're gonna see if it's correct with the actual word. Supervised would be if a human labels the data. This is done by the machine itself, so it's self-supervised. This is a very clever trick. We don't need any external evaluator to be able to learn in a supervised way. Humans do this too. Actually, the brain is based on cortical columns. There are thousands of cortical columns in the neocortex. The neocortex is a very homogeneous substrate. If you think of the neocortex as having different specialized regions, you are thinking of it in the wrong way, because the neocortex is actually fundamentally similar on all parts of the brain. The only reason why the front is different from the back is because the front got different input than the back. If you change the nerves from the eye, from the back of the brain to the side of the brain, then now the side of the brain will become the occipital lobe. That's because of the homogeneity in the substrate. That's because it's similar all throughout. And these cortical columns are predicting. They're predicting the next state. They all have their own abstract little world that they're predicting the next state in. Not equivalent to 1 pixel, equivalent to an abstract feature we might not understand. But there are thousands of these, and the whole brain is just doing prediction the whole time. So it's similar to GPT in this sense. They're both doing prediction. Now the interesting thing is that from this prediction emerges an ability to be able to imagine. Why is that? Well, if we know that A is related to B, then we know that if we have A, we must have B. And in this way, we can chain it together and we can create a sequence of data. So we can do A, B, C, D. That's a sequence of data. That's what these generative models do. They generate new data, sequences, these strings of data. And when we imagine things, we do the same thing. We string together pattern-matched elements. This is so key. This is so powerful because by imagining, we're able to explore the world in a much more free way. See, reality is constrained by many things. It's constrained by time, by resources, by physical laws. When we are imagining, we can subtract physical laws. We can go back in time. We can go to the future. We can plan ahead. We can remove gravity from our simulation. So we can get a lot of different diverse data. We can try out a lot of hypotheses in our head just by imagining. So imagination allows us to explore much more quickly than if we were bounded by reality. This is why I think introversion is often correlated to intelligence, because introversion is probably correlated to imagination as well. People who are introverted tend to be in their head more. They're able to more freely explore possibilities to their solution. This is so key. And GPT is able to do this. So we made a generative model and it seems like a gimmick, but actually it's doing something very key to human intelligence. But this is still system 1. To be able to get this model to actually think and go to system 2, we needed to generate these chains and then utilize it to find a solution. That's system 2. So we've seen this in models. We can ask it to do a chain of thought, think step by step. But we can also ask it to do a tree of thought, do multiple steps by steps. And see if we make sure the chains of thoughts are correct and valid, then we can just generate so many of these chains and one of these will reach the solution. If we just keep trying, we will find a solution. This is one of these methods. It's called brute force. It's super computationally inefficient, but it can work. With enough computation, with infinite computation, we can solve any problem as long as we know the true value. Of course, we don't have infinite computation. So we need to constrain the search space. Dennis Absabis, the CEO of Google DeepMind, known for AlphaGo and AlphaFold, says that intelligence is the ability to constrain the search space. And I agree with him fully. So instead of creating every possible chain of thought, we need to constrain them. Find the right ones. Now, how do we do this? This is just intuition, based on system 1. So we already have a good system 1 model, which is GPT. This already has an intuition of which chains of thoughts are likely, because it's seen these before in its training data. It's seen correct chains of thoughts before. It already has an intuition about which ones are correct. So it's already constraining the search space because we have a good system 1 model. And as you will see every time, system 2 is totally dependent on system 1's capabilities. System 2 is just a specific application of System 1. We are making these trees of thought during test time. When we do find the right answer, in humans, we get rewarded by our limbic system. See, with pattern matching with System 1, we were rewarded by Hebbian learning, which was very local to the neurons. Now, reinforcement learning is not as local. It's more global. Next word prediction is very local. You need to predict every word correctly. Reinforcement learning loosens the constraints and it says you don't have to have every word correct, you just have to have the answer correct. It allows for much more flexibility and creativity. The human brain does it with its limbic system. When we get to the answer, then this chain of thought that brought us to the answer gets reinforced by the limbic system. And in machine learning, we can define the reinforcement learning any way we want. So in machine learning models, the way we define the reinforcement learning is going to define how we align the model. If we align it with human feedback, then it's going to be aligned to these humans' feedback. The reward function of reinforcement learning is the key of alignment. Specifically in GPT-4, they use reinforcement learning by human feedback, but the model only gets to hear whether the answer is correct. It doesn't get to hear why it's wrong. While the brain is able to investigate and look at what reasoning steps are incorrect. Now, O1 solves this problem. O1 trains the model to not only use chain of thought, it also evaluates the chains. It evaluates whether the elements in the chain are logically following. We can generate a sequence, for example, of a ball. We simulate a ball falling to the ground. So let's say it's a football. If it falls and it stops immediately, we know that's not logical. So if our chain of thought contained this simulation, then we know it's not a good chain of thought. A ball should bounce. Just from previous experience. The good thing about vision is that the true value of vision is very close to vision itself. What you see is what you get. It's not often that what we see is not true, except for like illusions and hallucinations. When we go to text, the true value is not always so straightforward. There's misinformation, there's ambiguity. And the way we deal with this normally in the real world is we use logic. And logic is something you can learn formally, which is system 1, but it's also something we learn just through living through the world. Something implicitly learned. And that's also system 1. So, as you can see, system 1 is the thing that generates chain of thoughts. It's the thing that is able to give an intuition for which chains of thoughts to generate. It's the thing that evaluates which chains of thoughts are correct. And it can even be the one that evaluates if the answer is correct, if we don't have a true value for the answer. So the whole system of system 2 is just system 1. There's no real distinction between the two, it's just applied in a different way. O1 was a necessary step, because I've seen an article saying that we've hit scaling laws limits with training of Orion, the next OpenAI's model, which is not based on chain of thought. So this is expected. A system 1 can only get so good. At some point, if you want to perform 100% on your test, you have to be able to understand. You have to be able to reason out of distribution. If you can only remember stuff in distribution, then you must hope that everything you learned is also on the test. And if there are new questions on the test that are different from what you learned, then you can never get 100%. So this is why there are diminishing returns before reaching 100%. Because they're missing this qualitative ability to reason out of distribution. And this is introduced by O1. This is why the response of OpenAI members is that they will keep seeing improvements. They are emphasizing there are no limits yet. Maybe scaling law limits, yes, but there are other ways to grow, which is in reasoning right now. And through this perspective sketched out here, it's easy to see the parallels between System 1 and unsupervised learning, and System 2 and supervised learning. System 1 using Hebbian learning and being in distribution, and System 2 being done by reinforcement learning and out of distribution. Seeing that the cognitive system of the human brain is so similar to the cognitive system of these models, if they're qualitatively the same, then we can expect them to reach human capabilities. This is why I take so much time thinking about this and explaining this. This is key to understanding how these models work and how they get to AGI. There are many misconceptions that would be gone if these concepts would be integrated.